Welcome back. Here is problem 3. A CNN Money article, College Cost Rise, on October 29, 2008, reports the total annual cost averages $34,132 for private colleges and $14,333 for public colleges. And they are 2008 figures, not today's figures. In an effort to compare those same costs in the state of New York, a sample of 26 junior students was randomly selected statewide from private colleges and 28 from public colleges. The sample means were $34,020 for private colleges and $14,045 for public colleges. By the way, this very problem came from our textbook. I didn't change anything here. Okay, 3.1. Suppose that the total annual costs for public colleges in New York State are normally distributed with a standard deviation of $1,510. Find the 98% confidence interval for the mean annual cost for public colleges. 3.2. Suppose that the total annual costs for private colleges in New York State are normally distributed. Period. Estimate the 98% confidence interval for the mean annual cost for the private colleges if the sample standard deviation was $2,150. What is the difference between 3.1 and 3.2? One is about public and the other is about private, but that distinction is not really a key issue here. I could have easily flipped those over. The key distinction is one problem uses the z-curve, the normal approximation, and the other problem uses the t-curve, the student approximation. Which is which? Do you remember that I emphasized period right here when I was reading 3.2? That was intended as a hint actually. Here in 3.1, the standard deviation of 1,510 came with the same sentence as the description of the population. You see, the total annual cost for public colleges didn't say anything, did not specifically say population, but here is indirect indicator, New York State, and that's normally distributed. So we are talking about the distribution of population. And the standard deviation, which was not specified as population standard deviation, but it came with the same sentence as population. So this is population standard deviation. This is sigma. Now for the second problem, we have this period. So this is about population. And then we have sample standard deviation was 2,150. So the latter is about sample standard deviation. There's a subtle difference between one and the other. And I could have made this problem even more confusing by taking this sample away and then put a little bit more description about the sample in the same sentence here so that you could see that 2,150 is sample standard deviation without specifying this sample right here. Here in the first problem, I did not specify whether this is population standard deviation or sample standard deviation. It came with the indirect hint that this standard deviation came in the same sentence as the description of the population. There's a subtlety there. Anyway, let's do 3.1. And here it is z-curve problem because population standard deviation is known. Well, but that's actually easy for me to say after talking about all the criteria. The key distinction between z or t was whether the standard deviation came with the same sentence as population or the same sentence as sample. It came with the same sentence as population. That's why it is sigma. Okay, initial picture. Now this is z-curve, and then we have 98% in the middle, 1% there, 1% there, and we are looking for endpoints. Let's go ahead with the answer key right away. End minus center over SC is here, and let's see, this is the z-score associated to 1% in left hand side, about negative 2.33, but I use a little bit more accurate figure using Mathematica. If you use statistical calculator, then you're going to get this kind of figure. If you use table, of course, you're going to get 2.33. Flipping the denominator and then flipping the mean, we have, well, approximate value, 13,381, about $13,380. And using the symmetry, flip this negative to positive, $14,708, or $14,710, approximately speaking. And here's the conclusion. Okay. All right, let's go to the next problem, the T-curve problem. And this is T-curve problem because we are talking about the sample standard deviation. So that's what it is. This is T-curve problem. This is S, not sigma. Initial picture, this is the key T-curve, but by naked eye, whether it is T-curve or Z-curve, you cannot really tell, but it is a T-curve. 98% in the middle, 1% there, 1% to the right, and let's look up T-table and then get T-score for this X2. If you do that, you're going to get this T-score, 2.485. Let's see, what is my T-table? So this part over here has to be 1%, and that's for degree of freedom of 25. Right here, 2.485. 2.485. Remember that there were 26 private college students here in this sample, so degree of freedom was 25. Anyway, from this equation, solving for x by this process, we have $35,067. Using symmetry, you get the other endpoint, $32,972. In the end, we have this conclusion. Once you begin the computation, it's not hard. End minus center over SC equals to the T-score or Z-score, and from the table you get T or Z-score. The hard part, the hardest part, is the decision making, whether this is T-curve problem or Z-curve problem. Now, in my exam, if you make wrong judgment, you're not going to get 0 credit. Typically, I give about 3-point deduction in 10-point problem in the exam. So if you use wrong table, get everything right, depending upon circumstance, you're going to get up to 10 out of 7, maybe 8 out of, excuse me, did I say 10 out of 7? 7 out of 10 is typical score I give. If you use Z-curve instead of T-curve and you have to use T or vice versa. Sometimes, based on another circumstance, I give up to 8 out of 10. But in any case, you have to make appropriate decision making. And the criteria, let me emphasize once again, this standard deviation came from the same sentence as the description of population. The second problem, this was explicit, but I could have made this a little bit harder by putting this standard deviation with the same sentence as the sample. That's how you can make the distinction between T or Z.